What role does sampling play in statistics? Sampling is a fundamental technique used to infer details about a larger population from a subset. It is crucial across fields like research and economics. Sampling allows for informed decision-making with minimal resources. This video explores its significance and methods. Understanding sampling is essential in statistics. It helps make inferences about a population using a sample. This technique is crucial in research and quality control. Sampling minimizes resources needed for data collection. It offers insights into various fields and phenomena. A sample is a subset of a population chosen to represent its characteristics. It allows conclusions about the entire population without studying every individual. Sampling saves time and resources. It's cost-effective for gathering and analyzing data. This method is vital, especially for large populations. Sampling saves time and resources in data collection. It's impractical to study an entire population when it's large. Sampling provides a cost-effective way to gather information. It allows researchers to analyze data efficiently. This method is widely used in various research fields. Various methods like random, stratified, and cluster sampling exist. The choice depends on research objectives and population characteristics. Random sampling gives each member an equal chance. Stratified sampling ensures representation of subgroups. Cluster sampling is efficient for dispersed populations. Sampling is based on statistical theories like the central limit theorem. This theorem states that sample means approximate a normal distribution. It validates statistical analyses based on samples. Examples include political polling and quality control. These illustrate the practical use of sampling. Sampling involves selecting a subset from a larger population. It's used to draw conclusions about the entire group. The population is the whole group of interest. A sample represents this group to minimize bias. Inferences are made assuming the sample reflects the population. In simple random sampling, each member has an equal chance of selection. It's achieved using random number generators. This method is unbiased and straightforward. However, it may be impractical for large populations. There's no guarantee of complete coverage in such cases. The population is divided into subgroups or strata. A random sample is drawn from each stratum. This ensures representation of diverse subgroups. It's useful for populations with varied characteristics. However, it requires prior knowledge of these characteristics. Researchers select every kth individual from a list. The starting point is random, with k being a fixed interval. This method is simple and practical. It's effective for ordered or well-structured lists. However, patterns in the list can introduce bias. The population is divided into clusters, like geographic areas. A random sample of clusters is selected. All individuals in chosen clusters are included. It's efficient for geographically dispersed populations. However, it may introduce higher sampling error. Researchers select individuals who are readily accessible. This method is quick and low cost. It's suitable for exploratory research. However, it may not represent the population well. Bias is likely with convenient sampling. Used in social sciences for hidden populations. An initial participant recruits others, forming a snowball. It's useful for marginalized groups. However, it's dependent on referrals and may not be random. Bias and lack of representation are concerns. Researchers select individuals meeting specific criteria. It's useful for studying experts or subgroups. However, it may lack representativeness. Researcher bias is a concern. This method is efficient for focused research. Random number tables and generators are tools used. They help select random samples by assigning numbers. Tables are pre-generated while generators are software tools. Both methods ensure unbiased selection. Consistency in method use is crucial for accuracy. Random number tables contain pre-generated digits. Researchers start at a random entry point. They read digits sequentially to select sample elements. This method requires careful matching to population elements. It ensures randomness in selection. RNGs are software or hardware tools producing random numbers. Define the range and sample size needed. Use RNG functions in software to generate numbers. Match these to population elements for selection. This method yields a random sample efficiently. Ensure random selection methods produce unbiased results. Consistency in sampling methods is key. Verify the sample size and population coverage. Use reliable RNGs for accuracy. Avoid patterns in random number table use. Stratified sampling is suitable for diverse teacher populations. It ensures representation of different subgroups. Cluster sampling is an option for institution-based selection. Sample size depends on confidence level and margin of error. These methods offer insights into job satisfaction. Determine sample size using confidence level and margin of error. Population variability affects size calculation. Larger samples offer precise estimates but are resource-intensive. Balance research objectives with practical considerations. A well-calculated sample size ensures reliable results. Stratified sampling captures diverse teacher experiences. It improves representativeness and precision. A sample size of 384 is practical. It provides a balance between precision and resource use. This approach enhances the study's external validity. In conclusion, sampling is essential for making accurate statistical inferences while balancing precision and resource efficiency. By understanding and applying the right techniques, you can select the most effective method for any study. Use these insights to strengthen your research practices and achieve more reliable outcomes. If you have any questions, please feel free to reach out via WhatsApp or email. Thank you.